Okay, in chapter 13, section 1, we're going to look at graphing vector functions. And the first problem, it's a short video, I think it's about 4 or 5 minutes, where the professor is going to show you how to graph a vector function. So basically, these functions are parametric, which means they're dependent on a fourth variable like t. And so you'll have x as a function of time, t, time, usually it can be time. Could be anything though. Y is a function of time, and then z is a function of time. And what you have to do is pick t values, and then you solve for x, y, and z. So these are just functions like the first one. That's not a great example. Their x value is 4 cosine t, their y value is 4 sine t, and their z value is t. So let's say we pick t equals 0 in this example. Well, x, which is 4 times cosine t, cosine 0 is 1, so you get 4 times 1, you get an x value of 4. And then for the y value, it's 4 sine t, but time is 0 in this case, and sine of 0 is 0, so you get 4 times 0, which is 0. And then z is t, but we plugged in t is 0, so you get 0. So you get an ordered triple, 4, 0, 0, that you have to plot in 3 dimensions. So we have x, y, and z. This would be 4 units in the x, 0 in the y, 0 in the z. So this thing's going to sit right here on the x, y plane. But this is why it's cumbersome to plot parametric curves, because you have to do this many times. You have to pick like 10 or so t values just to get the sense of what this curve is doing. And he goes through that, and you can just pick more and more t values. And the picture he ends up getting for this particular curve is a spiral. So it turns out if you pick x as cosine and y as sine, that would be a circle in the xy plane. But then so if z wasn't there, then this would just be a circle. 4 cosine, radius 4. You have 4 cosine, 4 sine. But when you add z as t, this thing also starts to climb off the xy plane. So it's not only going to be circular, but it's going to start to climb up and just keep spiraling around. Okay, so it says it's similar to a spring. Well, a spring has that spiral shape, so we would say true. Sure, it looks like a spring. Okay, that's problem 1. In problem 2, again, you can watch the video and you'll kind of see what it looks like, but it says it's a hyperbola on the xy plane. If you see what he graphs at the end, it looks like 2 lines. It looks like an X, so that one would be false. Okay, so here's our spiral shape again, but we're going to explore it in more detail. So it says sketch the curve whose vector equation is 6 cosine 6 sine plus 5t. So this is really similar to the first problem. Okay, first we're going to break it down into x, y, and z. So the x part of this equation is just the 6 cosine t. The thing in front of I is your x. The thing in front of the j term is your y. And then whatever's in front of your k term is the z term. So we have 6 cosine, 6 sine, and 5t. Okay, then they say since x squared plus y squared equals 36 cosine squared plus 36 sine squared, so all they did was square, so if x equals 6 cosine t, then x squared would be just square both of these things. 6 squared and then cosine squared t. And you can actually square that 6 and call it 36 cosine squared t. Okay, and then same with the y term, they squared that, so they're going to get 36 sine squared t. Well, it turns out that based on this property, sine squared t, actually let me write it like this, cosine squared t plus sine squared t equals 1. So if I have 36 cosine squared t plus 36 sine squared t, which we do have, that's going to equal what? Well, you can factor out 36, and you're left with cosine squared t plus sine squared t. And that whole parenthesis, based on this up here, equals 1. So this would just equal 36 times 1, which is 36. Okay, and how did we get that? We squared x and we squared y and we added them. So this equation becomes x squared plus y squared equals 36, which is the equation of a circle. So x squared plus y squared equals some number squared, which we call radius, is the definition of a circle centered at the origin of the xy plane in this case. Okay, so then it says, so it would move counterclockwise around this circle defined by x squared plus y squared equals 36, but because z equals 5t, that's going to lift the circle above the xy plane and make it go up and around. So if that z term wasn't there, this circle would just sit there and it would just literally go around and around this circle forever as t increased. But because there's a z term, this thing's going to lift off of the xy plane and become what we call a helix. Okay, that's problem 3. Okay, in problem 4, they're going to have us intersect a circular cylinder with a plane. So they drew it down here. This curve C is the intersection of those two shapes, and you can see it will look very nicely like an ellipse, like this. Okay, so how did they get that? So it says find a vector function that represents the curve of intersection of the cylinder x squared plus y squared equals 9 and the plane 4y plus z equals 13. So the first thing they want us to do is plug in that this x squared plus y squared equals 9, so we can get that right from the problem statement, when z is 0. So again, you can kind of see it down here, at the xy plane, you have a circle of radius 9. So it's centered at the origin, and its radius, actually its radius is not 9, radius squared equals 9, so the radius is 3, the square root of 9. So at the xy plane, there's this radius 3 circle. Okay, let's see what else. So we can break this down into, we just saw in the previous example, if we change x to 3 cosine and y to 3 sine, when we square those, we're going to get 9 cosine squared t plus 3 squared, which is 9 sine squared t. And we said this equals 9, and this should equal 9 if we did this right. We'll factor out a 9. We're going to get cosine squared t plus sine squared t. But this whole thing equals 1 based on that property I gave you in the previous problem. And so it truly is equivalent. 9 equals 9. So that is a fair substitution. We can change x to be 3 cosine and y to be 3 sine, and that would be, when I square it, equal to a circle of radius 3. Okay, so if I can make that substitution, then I can substitute those into this equation. So we can say, okay, the equation of that plane that's intersecting the cylinder is 4y plus z equal 13, and they solve for z, so let's show this. To solve for z from this circled equation, you would take 13 minus 4y, but we're substituting y as being 3 sine t. So we're trying to find what's called a parametric representation of this curve in Cartesian coordinates, x and y, by doing this substitution here. So we're going to get z is really 13 minus 12 sine t. And that's what they show here. Oops, just covered it up. So that is what they show right there. Okay, so the parametric representation of this curve would be x is 3 cosine t, we saw that. Y is 3 sine t, we saw why that was. And then z is 13 minus 12 sine t, we just derived that. and they're putting the restriction that t should vary between 0 and 2 pi. Okay, then we can just put all that together. So put your x term in front of the I coordinate, put your y term in front of the j coordinate, and put your z term in front of the k coordinate. So that is the vector equation in parametric form, where you have I, j, and k, which are representative of the x direction, y direction, and z direction. Okay, problem 4. All right, problem 5. Find the domain of the vector function. Enter your answer in interval notation. So the domain of a function is going to break down if we divide by 0 or if we have the square root of a negative number. So here's what we're looking out for. Divide by 0 or the square root of a negative number. If we get one of those two conditions, we're going to have a breakdown in the domain. So we just have to look for that. So it says the vector function is, let me write it bigger. The vector function in parametric form is t minus 2 divided by t plus 2 times the I component, the unit vector I, plus sine of t in the j unit vector direction, plus the natural log of 36 minus t squared in the k unit vector direction. Okay, now the sine of t is continuous for all t. There is no t value that's going to make that breakdown. Okay, so sine function, you might recall, it's going to look like, it starts at 0 and it goes like this, and it goes forever, and then it goes down here forever. So completely continuous, no t value is going to cause a problem, so I can ignore that term. Now the x term, I do see a problem. If t equals negative 2, imagine if t was negative 2 right there, we would get a divide by 0 error. We'd have t minus 2 on top and 0 on the bottom. So we have to record over here, let's do it over here, t should not equal negative 2. I'll get divided by 0. But that is the only number that causes a problem for the I component. Okay, now for the z component, we have natural log of 36 minus t squared. Now it turns out that natural log of any x, any value, is only defined if that argument is bigger than 0. It can't even equal 0. You can try this on your calculator. Type natural log of 0, you'll get an error. Type natural log of a negative number, you'll also get an error. So not only does it have to be positive, but it has to be bigger than 0. So we have to make sure that this whole thing is bigger than 0. So let's set that up. Make the argument of the natural log force to be bigger than 0. Add t to both sides, t squared to both sides, and then take a square root, adding a plus or minus to both sides. And this is interesting. This is actually going to give us two equations. It's going to give us the positive side will keep the direction of the greater than sign the same. And then square root of that, so it becomes t. And when I take the negative square root of 36, I have to flip the inequality and make it look like that. Okay, so we're going to get t has to be smaller than positive 6. T has to be smaller than negative 6, and t has to be bigger than negative 6. So in essence, t is sandwiched by 6 and minus 6. So another way to write this is t is sandwiched between minus 6 and 6. And negative 2 is in that interval. So let's put a number line out here just to see where we have what this is looking like. And let's put 0 right in the center. And our numbers of interest are minus 6, 6, and negative 2, which would be over here. So basically our function is defined not including 6 all the way up to -2, but not including it. So we use parentheses to exclude things. Then parentheses excluding -2 all the way up to +6. So in one dimension, to just show the t values, I can have anything between -6 and -2, and then anything between -2 and +6, but nothing smaller, nothing bigger than that. So the way you would write that in interval notation is right here. -6 to -2 with parentheses, union, so this U symbol means union. So you're unioning two sections of the number line, and then -2 to 6. So that's this section here, and that's this section here. Okay, so not a ton of arithmetic there, but you just have to remember how domain is defined. Okay, for problem 6, it says sketch the curve with the given vector equation indicating an arrow the direction in which t increases. So again, to do this, you would want to pick some t values and then get values for sine 6t and t. And basically, let's look at this. So sine of 6t. So in the, let's see here. The x direction is t. The y direction is actually the x value. This is kind of weird, where x is equal to sine of 6t. Well, quick trig review. We call this number in front of t omega, and we know that the period of a sine function is 2 pi divided by omega. So the period is 2 pi over 6, which is pi over 3. So by the time this thing hits pi over 3, the sine curve should have gone through one entire cycle. And let me divide this in half, in half, and in half. So here's what this is going to look like. And it's also varies only between 1 and -1. So the sine curve starts at 0, goes to 1, back down to 0, down to -1, back up to 0. And then it's going to repeat this. And it's going to repeat this over on this side. Okay, so your x value as time marches on is going to go from 0 to 1 to 0 to -1 to 0 to 1 to 0 to -1, etc. So it's going to bounce back and forth between those numbers. And it's reflected in the graph as a y direction, actually. So this y direction, the x, so x is on the horizontal here, this x is always going to bounce between -1, 1, -1, 1, as we showed here. But your y value is actually, as a function of t, your y value equals t. So you're going to get as t marches along, y is going to equal it. So if time is 1, y is 1. If time is 2, y is 2. If time is 3, y is 3. So it's a straight line. So your x value is going to continually bounce between -1 and 1, but your y value is just going to get bigger and bigger and bigger. So, and that's reflected, and it's going to be negative too, so I can go this way. So it's reflected here. So when y is negative pi over 3, when time is negative pi over 3, your y value is negative pi over 3. But your x value is whatever sine of negative pi over 3 is times sine of 6. So sine of 6 times negative pi over 3. So your time, so basically your curve is going to go like this. It's going to, in the x direction, bounce between -1 and 1. And in the y direction, it's going to just get bigger and bigger and bigger. It's going to go up. And again, you'd probably want to pick some t values and just get a bunch of x, y coordinates and then plot them, and you'll see how it goes. Okay, problem 7 is where we're going to actually take this to a plotting software. So again, you can do these by hand. If I show you this problem on another software, I would not ask you to do it on a test because we don't allow other softwares on the test. So if I am going to another software to solve a problem, chances are good you will not see a problem like that on the test. Okay, you could plot these by hand, but again, I don't encourage it because it's a lot of work. If I can find other softwares where you can program it, I'll show you that. But there's a lot of free tools where we can do this just to get a sense of what's going on. So the vector function, parametrically speaking, is t sine t and 3 cosine t. Just writing it bigger so we can see it. So what you want to do is, again, go to GeoGebra and pick like, you can Google, I think that's the wrong one. Here it is. Okay, so you can Google parametric curve 3D for GeoGebra, and you have to click into this. So they'll have A highlighted also. This is just like a general graph they have. Just click that off. You don't want to see that one. But they already have a parametric curve set up. It's called B equals curve. And you just have to type in. So if our problem was x is t, y is sine t, z is 3 cosine t, you just have to type t, comma, the y value sine t, the z value 3 cosine t. Then you have to tell it the variable, which is t. Then you have to pick a t range. So you'll notice this was exactly our x coordinate. This was exactly our y coordinate. This was our z coordinate. This is the variable that we're using. You have to leave that in there. It'll default to that, so just leave it in there. And then these two numbers represent the t range that you pick. Okay, and it will populate that. And then you can click in here and you can zoom out and it will populate this. Let's see if we can pick a bigger number for t so we can see more of this curve. Let's go with 20. And you have to kind of click away to get it to re-render. But you can kind of see how it's spiraling. That's a pretty good shot right there. How it's spiraling around this x-axis. So we just go back to our options, and clearly it's going to be this top left one. So this is a function where, you know, use the tools and get a sense of what's going on, or you can pick t values and solve like I showed in that first problem. You get an x, a y, and a z, and then you have to plot in 3 dimensions. So that's how we would do that problem. Okay, so this one's kind of neat. Problem 8, same thing. So it's t cosine t, y is t, and z is t sine t. And I believe I already have that one plotted right here. So t cosine t, t sine t, t is your variable. Let's try 20 again. I like that, how it gave us more points last time. So you can see how it updates. X is t cosine t, y is t, z is t sine t from 0 to 20. And you can see it's kind of this nice like expanding spring kind of thing. And it's going along the y-axis. So we can go back to our possible pictures, and clearly it is this one right here. So with the tools, it can be pretty quick and easy to get the answer here. Okay, problem 9, we cannot use GeoGebra, not going to help us here. So it says find a vector function r of t that represents the curve of intersection of the two surfaces. So it says the cylinder x squared plus y squared equals 4 and the surface z equals xy. So we're going to do the same thing we did before. We're going to let x equal, if this is 4, the number you pick is the square root of 4, which is 2, and that number is going to go in front of cosine t. And then y is also going to get a 2 in front of it, and we're going to pick sine t. And we already went through the argument of this. If I square those two, I get 4 cosine squared, 4 sine squared. I can factor out the 4, and I'll get basically x squared plus y squared equals 4. But now, so that is part of the answer. In fact, x is 2 cosine t. The y term in front of the j component is 2 sine t. The tricky one is getting the k component. Well, it says the intersection is z equal xy. So what we have to do is substitute in 2 cosine t for x and 2 sine t for y. And we can do 2 times 2, that would be 4 cosine t sine t. Well, there's a double angle formula that says if we have some number cosine t sine t, we can write that as a over 2 of just sine of 2t. So I can double the argument and have the amplitude of the number in front. So if I had a 4 out in front, we're going to have that. So z is really 4 over 2, which is 2 sine of 2t. That is your z component, 2 sine of 2t. And we'll put that in front of k. So you just have to type these parametric equations in front of I, j, and k. That would be problem 9. Okay, last problem in this section. It says the curve with vector equation r of t equals 5t squared, actually write this bigger. R of t is 5t cubed in the I direction plus 6t cubed in the j direction plus 7t cubed in the k direction. And if you go to GeoGebra and plot this, so again you can see on the left 5t cubed, 6t cubed, 7t cubed, t is the variable, 0 to 3, and you'll get this curve right here. And you don't have to pick very big t's because t cubed is going to be 27, and then you're either multiplying by 5 or 6 or 7. So that would be the equation, that would be the resultant parametric curve, and it clearly is a straight line. So we'd go back and say, is it a line? It sure is true. And that will complete section 13.1.